So this video marks the start of Chapter 6, and in my opinion, Chapter 6 is the toughest unit out of either semester of AP Stats. The test average for my classes tends to be one of the lowest of the whole year, usually the very lowest overall. And it's because there's a lot of content, like a lot of challenging content that's kind of packed into this unit. There are going to be three sections here, 6.1, 6.2, and 6.3, and each one covers a different aspect of the concept of random variables, which is kind of the big picture idea of what's going on in this unit. But each section does it in a different way, and it's going to feel almost like three separate sections here lumped into one chapter. So there's going to be a lot of content coming your way here that you're going to need to practice and you're going to have to study. So make sure you're taking good notes, rewatching these videos, etc., to really make sure you're staying on top of the stuff we're covering here. So with that little spiel out of the way, let's go ahead and jump in with the concept of a discrete random variable. And that title in of itself should be a little bit like crazy, like what does that even mean? So we need to start by defining some terms. First of all, what is a random variable itself? A random variable takes on numerical values that describe some chance process. Now, even that definition, when you read it, like, what does that mean? It's still kind of unclear, in my opinion, what's going on. A random variable is basically a tool we use in statistics to count something or to track something. So you guys know how we use variables in math in general. I picture random variables kind of like super variables that we use to track stuff related to probability. So example, I could look at a random variable. And by the way, the variables that we use, just like with probability, we use capital letters to represent random variables. I may be interested in knowing how many of you did your homework last night in class, so I could have the random variable x, which is the number of students who did their homework on a given day. And that value of x can change from day to day. It could be as low as 0, where nobody at all did their homework, and it can be as high as the number of students in the classroom there. We could rattle off a bunch of different examples of random variables, but that's the basic idea. You pick something that you're interested in, that you're going to track with a variable, and then you find the probability for the different options that that variable can have. That is called a probability distribution. So a probability distribution tracks the values for a random variable along with the probability for each value. This probably sounds a little familiar. Probability distributions are very similar to what we called probability models earlier on in the last chapter. And yeah, you can have a probability distribution. They're going to look like tables where you have the values that are possible along with the probabilities that go with each one. And in this section, we are learning about not only random variables, but a specific kind of random variable called a discrete random variable. Discrete random variables are random variables where there are gaps between possible values. So what does that mean? Well, if I look at my example up above here, the number of students who did their homework on a given day, there could be 0 of you, or 1 of you, or 2 of you, or 3 of you, etc. There couldn't be 2.7 of you who did your homework. So you kind of jump from 0 to 1 to 2, and the decimals in between aren't allowed. People will sometimes think like, oh, okay, it's just no decimals. But that's not always true either. A good example of that would be if I were going to look at amounts of money that you guys could pay for something. We could have where it could be like $3.35, or you could pay $3.36, or you could pay $3.37, but you couldn't pay 3.35918 for a item. That doesn't work out. So you still have gaps between here and here and here. This would still be considered a discrete random variable. So, okay, what isn't a discrete random variable then? Say I wanted to measure the length of something, okay? So I'm looking at different cats and I want to know how long they are. Well, when I do that, I basically, depending on how like precise I want it to be, I could always go one decimal spot further and be even more precise on that. So length, weight of things, like how much things weigh, heights, those are all examples of variables that are what are called continuous random variables, where there are no gaps. Time, if you're timing something, would be another. It's just a matter of how precise you want to be. But this section, 6.1, is going to focus primarily on discrete random variables, which are going to be variables that have those gaps in between. And as our kind of example here that we're going to run with, normally I would actually poll you guys and get the class data, but I can't do that because it's a video. So I made up fictional data right here, looking at the number of children in the households of different statistics students here. So the least number of kids, presumably, because you're a student, so there has to be at least one kid there. So the least possibility is one kid, and there were 3 out of 20 kids who supposedly said that. 6 of you said, 6 out of 20 said there were 2 kids in the household, etc., etc., etc. So this is a discrete random variable, takes on the values 1, 2, 3, 4, 5, or 6 or more. There is nobody who has 3.7 kids in their households. So show that this probability distribution for X is legitimate. This is going to feel a lot like those probability models we did last chapter. You need to do 2 things. All probabilities are between 0 and 1. In other words, there's no weird negative probabilities or probabilities over 1 that can't exist. That's true. Those are all good probabilities. And then do they all add up to 1 total? Have we accounted for all possibilities in this problem here? So like, did I miscount or write something down wrong or whatever? And if you add all these probabilities up, they do in fact equal 1. So that is good. That means it's a valid probability model. Is 5.617 a possible value for X? No, you can't have decimal children. So this is an example of a discrete random variable. That's what it means. We're tracking, we're counting. Basically, a lot of times variables count things. They count the number of children in a given household. All right, so let's go ahead and move to the next page, but I'm going to tab back and forth between these because there's a lot going on. For this next problem, I ask you guys to make a histogram for the probability distribution of X. So we're going to make a histogram for this table right here, and I'll do this on this slide where there's a little more space, and so I can actually see the thing, but this is part C right here. When you want to make a histogram for a probability distribution, or graph probability distribution in general, along the x-axis is going to be my variable x. And then what I'm going to do is I'm going to graph the probability of x, so p of x, along the y. So the higher probabilities will go higher. In my problem here, my lowest value is a 1, and I go all the way up. 6 or more makes things a little weird. If I'm going to graph this guy, and I'm almost off the grid anyway. But when you make a histogram, when you can only equal whole numbers here, it's actually, I think, easiest if you sandwich the bars. So like the bar for a 1, I'm going to start it at like a 0.5 and go to a 1.5. Because if I put a bar just in between 1 and 2 like this, we know from learning about histograms that this counts 1 but doesn't count 2, but then things get weird. Like it's harder to understand when you look at it. So I'm going to make my bars go in between and kind of center them along each whole number here. And then I'm going to make my probabilities go up by 1/20th, so 0.05, 0.10, etc. So I'm going to pause and come back with a picture for you guys. All right, so I've got a little histogram here along with an explanation because it did also say to describe the distribution in the problem. So when you describe the distribution, you're doing spec from chapter 1, shape, outlier, center, spread. Now, when you read through my answer here, I'm talking about the distribution of number of children. It appears to be skewed to the right. Values vary from 1 to 6, and I use the table to get that. You can just look at it and see. I also said the median appears to be at 3. If you didn't want to be super firm in that, I actually know it's 3 by looking at the number of values in each. You could just say the center appears to be around 3 and not get as specific as I did. I didn't mention outliers in my description right here, and that's actually an okay thing. Probability distributions rarely have outliers, so it's not something that you're frequently needed to do. There aren't any, so saying no apparent outliers would be totally fine, but I chose to just not mention them at all since they weren't relevant to the problem here. But that would be a good histogram and a good explanation of part C. When you have a probability distribution naturally, something you'll be asked to do quite a lot is find probabilities. And this again is going to work like we did last chapter. We're just finding probabilities out of a table. So part D says, what is the probability that a randomly selected student has at least 3 children in their family? All you're going to do for that, at least 3, means it could be 3, or it could be 4, or it could be 5, or it could be 6 plus. We're just going to add those up and they're mutually exclusive, so we don't have to subtract anything. If you add those, for that one, you're going to get, it looks like 11 out of 20 or 0.55. So that is the answer for part D. So moving on to part E, they ask for another probability. What is the probability that a randomly selected household has more than 3 children? How is that different than part D? And I actually want to go ahead and put symbols on this now that I'm back on this page right here. This one asked us to find the probability that it was at least 3. And we found out that that was going to be 11 out of 20. This one just straight up says more than 3. So this is the probability that X is just greater than, not greater than or equal to 3. So 3 is not allowed. Is how that's actually different, and finding those not very difficult. You're just going to look at this and say, okay, I don't want 3, I just want 4, 5, 6, and that appears to be 6 out of 20 for this probability. So the next one is bringing in the concept of conditional probability. And conditional probability is, it says it's given that there are at most 3, we want to find the probability there are exactly 2. So we're going to find the probability that X is 2, there are 2 kids, given that there are at most 3. So we already know X has to be less than or equal to 3. Best way to do a problem like this is just the cover up table method here. We're not going to use a conditional probability formula because we can just cover up the part we don't want. So it's given that there are at most 3. That means that all the rest of this table with 4 kids, 5 kids, 6 kids, that all doesn't matter to us anymore because we know that it's got to be this part of the table. So for this one, I think I'm going to make these decimals. It'll be easier to do my calculations this way. And if you look at my decimals, we are not working out of the total of 1 anymore because it's given that there are at most 3. So what I'm going to do is I'm going to add these up right here for my new total. That's going to make, if you add those up, a 0.7. So if you add up these parts right here, that area adds up to, that probability adds up to 0.7. And they asked for the probability of exactly 2. That's going to be 0.3 out of that 0.7, which as a decimal is about a 0.429 chance. So if you know there's going to be at most 3, the probability of it being exactly 2 is about 42.9%. So you can do conditional probabilities just like you normally would. And then this last one right here, what is the average number of children in a family in this class? I've packed a ton of stuff into this slide right here. If you think about it, what people will do that is incorrect. So think about how you would actually find the average right here. Something I see that's incorrect is people will just be like, oh, I'm going to take 1, 2, 3, 4, 5, 6. I'm going to average those and I'm going to get 3.5. I'm just going to straight up average those numbers. That's not okay to do for a couple of reasons. First of all, you have to take into account how many people are in each of the groups right here. It turns out there's actually 3 kids that said 1. So if I wanted to find the average of this data set, I would have to look at it as a 1, a 1, a 1. Then I would have a 2, a 2, a 2. I'd have 6 of those. And I'd have to do that for each of these to get my actual total for the average. Well, that's a little bit annoying to do. So what I'm going to do is do like, I have 3 1s. So I'm going to do 3 times 1 plus I have 6 2s. And then I have 5 3s. I have 2 4s. I have 3 5s. And I have 1 6 or more. So I'm just going to call it a 6. The 6 or more does make it a little bit weird here. But let me go ahead and treat it like it was just equal to 6. And if you add all those up, that makes 59 out of my total of 20. So the actual average for this class is like 2.95. It's a lot less than you would have gotten just by averaging these numbers right here, because the numbers on the bottom side of the graph are more popular. So yeah, that's the actual average right there. I'm going to show you guys later in these slides. I can't remember where I put it, but instead of just basically adding them all up and then dividing by 20, what you can do instead is turn these into probabilities. So just 3 times 1 over 20, 2 times, there's 6 times 2 over 20, times 3 over 20, etc. And, oh wait, I'm doing that to the wrong part, I'm sorry. Let me backtrack on that thought. I can take the probabilities. So instead of doing, I have 1, I can do that times 3 over 20. I have 2, I can do that times the probability of 6 over 20, make this a 5 over 20, etc. And it gets me the exact answer without having to divide afterwards. So I'll come back to that when I show you guys the actual formula for finding an average. So let's keep it going here. We spent a lot of time on that slide. And before I actually define the concept, the big concept we're talking about, working towards right now, is the idea of something called an expected value. Let me show you guys a hypothetical situation right here that I see a lot of kind of conversation about in class where it's not an obvious answer for kids. So we're going to do a hypothetical game right here where you're going to roll a die from 1 to 6. Okay, so you're going to roll a die. If you get a number from 1 to 5, you get $20. So if you roll a 1 through 5, you win $20. If you roll a 6, you lose $1,000 and you're obligated to pay that amount. Would you roll the die? Okay, that's what I want you to think about and come up with an answer for. Would you roll the die if a 1 through 5 meant $20 win and then a 6 means $1,000 loss? So get that idea in your head with what you personally would do. Usually when I do this in class, it's surprisingly close to a 50-50 split in terms of what people would do. There's not like a common consensus generally in this problem, which is crazy because there totally should be. There's like a right answer to this problem in my mind. So without knowing what your personal opinion is going to be, what I'll see is kids will say things like, well, I'm probably going to win. There's, if you calculate it, an 83% chance I win $20. The odds are in my favor. So yeah, I'll roll the die. But there's the other side, the correct side of things, that looks at that and says, well, sure, I could win $20. And even if it's not that likely, it's only $20. If it's not that likely I'm going to lose, I'm only going to win $20. If I do lose, I'm going to lose $1,000. And that's going to be pretty devastating to lose that much money. Oh, I don't have $1,000 to give you for a bet like this. So you have to weigh not only, what is more likely, but you have to give weight to what the reward is, okay? To give you like a more extreme example, let's say we were going to pick a number from 1 to 100. And if you got a 1 through 99, you got $1. And if you rolled 100, I was going to like run over your leg with my car. That's a terrible bet to take, even if it's not very likely that you're actually going to get that 100 right there. Winning $1 doesn't compare to the like awful like getting your foot run over with a car. That's just terrible. So you have to give weight somehow to the like what's more likely to happen. And if we look at this problem, they tell us to create a probability distribution for this problem. We're going to call X the amount of money that we win. And X in this problem only has two possible values. X can take on the value of positive 20. It can also take on the value of negative 1,000. So X and the probability of X. There's a 5 out of 6 chance you win $20, but there's a 1 out of 6 chance you lose $1,000, which would just be awful. So the answer for this is no, you should absolutely not play this game because the risk is so much worse than the reward if you actually win. Winning $20 is not worth losing $1,000. So you can see kind of in your gut, like, okay, yeah, well, what if it was a smaller number? Like, where would the cutoff be? Or like, what's the probability have to be? Clearly, there has to be a point where it becomes an okay thing to do. What we're working towards right here is the idea of an expected value. We have to be able to know how to find an expected value. So the symbol that we use for the expected value of a random variable x, there are two that you'll frequently see. One is capital E parentheses x. This means expected value of x. You'll also see the symbol mu with an x on it because an expected value is basically an average. So what does an expected value actually mean? I'm going to leave this because I think I make you find this example. No, I do that. Oh, I'm going to do it anyway. So the formula for an expected value is going to relate to what we ended up doing in that number of children problem. To find an expected value in general, what you do, and this is on your formula sheets, you are going to add up each value, remember we use x with an I on it for value, times the probability of that value. Okay, so you see the notation xi, and then you see pi for this. That could be x1 times p1, x2 times p2, etc. So it's each value times the probability of that value, and then you add them all up. So let's talk about our expected value for our problem right here. Well, winning $20 has a 5/6 probability, but then losing $1,000 has a 1 out of 6 probability. And if you actually do the calculations on this, you end up getting the number -150. That is the expected value for this problem, -150. Now think about what that means, because I'm going to give you how you interpret an expected value in just a minute. But if you think about that -150, there's never going to be a time where you roll the dice and you owe $150. That can't happen in the problem. You either win 20 or you lose 1,000. Those are the only possibilities there. So the way you have to think about this, it's easier again to think about it written out. So like, okay, you would expect that 5 out of every 6 times you play, you get $20. But then that 6th time, you lose $1,000. It's not going to happen like that predestined because you guys know, like short term, that's not what occurs. It doesn't have to go in that order. We could have like a string of 12 in a row where we win, but you could also have a couple -1,000. So you're going to see basically this setup right here. You'd see this and you'd see another setup of the same thing in the long run. After you take all those 20s and all those -1,000s that you could win, they're going to average out to about a -150 every time you play. -150, -150, -150. Okay? So every time you play, you're basically paying up $150 on average. That's what an expected value does. It looks at the long run. If you play lots of times, yeah, you got those $20 bills that you won here and there, but you've also got those $1,000 like hits that you took less frequently. And if you average all of those, they average out to about negative $150 per roll. So, what does expected value mean? Over many trials, and this is the part that people forget to mention, so like underline that, emphasize it in your notes. Over many trials, the average amounts won or lost will be, or won or lost per roll, I should say, is $150. I don't like that very much. Basically, I tried to do like a general thing over here. The average amount lost per roll, if I'm talking specifically about the dice problem, would be right here. But when you interpret a expected value in general, like a little script to use is like over many trials, the average blank will be blank. And you can just give context for the problem. So we'll do other examples and you guys will see how that actually works. But the idea of talking about over many trials or in the long run is really important for expected value. So let's look at another example right here. In a game of roulette, you can make a $1 bet of something called a corner bet. I've never played roulette, so I guess it explains in the problem what that means, but it's whatever. It's a bet you can make in roulette. You're going to make a $1 bet. And if you win, you get your dollar back plus 8 more. If you lose, you lost the dollar that you started with. Okay? So you either pay $1, you either lose that dollar if you lose the bet, or you get your dollar back plus $8. So you profit $8 right there. And if we look at this as an expected, a random variable, our random variable has two possibilities. Either you're down $1 or you're up $8, where X is the gain from a $1 corner bet. And they've diagrammed in this kind of little table right here, there's a 34 out of 38 chance that you lose $1, that you don't win your bet. But there's a 4 out of 38 chance that you win $8. So they ask us to find and interpret the expected value of X. To find the expected value, all you do is you take each value times the probability that goes with it. And if you actually calculate this guy isn't too bad to do by hand because that's negative 34 and that's 32. You're going to end up with negative 2 over 38, which is a negative 0.052. 0.053 if you round it. So negative 0.05. I guess I'll do 2 decimal spots because it's money. Okay? So that is a negative 5 cents. What does that mean? Well, when you play the game, you're either losing $1 or you're getting $8. Those are the only two possibilities. But if you take all those negative 1s and all those positive 8s, they'll average out, if you do it enough times, if you sit there playing for a long time, they're going to average out to a 5-cent loss per spin or per time you played. So if you play many roulette games, if you place many $1 corner bets, there's the context from the problem, you will lose an average of 5 cents per bet. So if you play this game 1,000 times, you would expect to lose 5 cents every time you play it on average. You're going to come away losing that's $50 over the course of 1,000 bets. Okay? Expected value doesn't take on a value from the problem all the time. It's just an average if you play many times of what's going to happen for your outcome. Okay, you'd lose an average of 5 cents per bets. So any game in a casino you find, any game, guaranteed, will have a negative expected value. If the game had a positive expected value, it means that you're going to make money after you keep playing it, and then the casino goes out of business. So casinos manipulate their odds or how much they pay you to make it so they are making money in the long term. Casinos aren't worried about the random person winning every now and then. That's actually good for business because people can see, oh, wow, they won. I might win too. But what they want is they want that expected value to stay negative. That way, in the long run, when lots of people are playing, the casino always comes out on top. So it's a good idea to be able to find an expected value for something just to know what you're getting yourself into. All right, so the last thing I wanted to do right here, and this video is feeling a little long. I don't know how long I actually have been, but I'm guessing this will be a longer one here. I want to talk about the expected value of the problem in our notes that we already did. And if I recall correctly, we already figured that out as 2.95. So we did basically, we would take 1 times the the probability for 1, etc. So let me at least start this one off here. 1 times 3 out of 20, and then it went like 2 times 6 over 20, etc. Just a different way of writing it, how we find our average. And I think it was a 2.95 when I did this. I didn't keep the answer, so I might be a little bit off right there. So forgive me and just plug in the correct number if that's not the exact of what we were supposed to get. What does this mean? So if you pick many randomly selected students, there will be an average of 2.95 children in their household. Now, obviously, nobody has 2.95 children in their house. That's okay. Expected value can be a decimal. It's just meant to convey the average over a large amount of possibilities. So that is a discrete random variable and how you find its expected value. So, this part right here, does the expected value for any variable have a value? No. And no, decimals are fine.